As I said, thanks for being here today. My name is Antoine. I'll be talking today about a project which is the brainchild of a collaboration between industry on the one hand and a number of academic institutions on the other. So on the industry side, today it's myself and Boyko Dadov. We both work for a catastrophe modeling company named AIR Worldwide. We're based of Boston. And on the university side, we have Timis Sapstis, who is a professor at MIT, Christian Lessig from the University of Magdeburg in Germany, and Henk Dijkstra, whom you definitely know because he's one of the organizers of this very event, right? So I personally started working on this when I was at MIT with Timis, and then recently joined AIR full-time to work on the project. This is ongoing work, so I'm going to be sharing with you preliminary results. And what that means is that you should feel free at any time during the presentation to interrupt me, ask questions, raise concerns, criticize, and so on. I mean, all of this is very welcome. So AIR is a catastrophe modeling company, and I should probably start by telling you a little bit about the essence or the raison d'etre of the catastrophe modeling business, which is basically to quantify the probability of an extreme weather event, such as a hurricane or an earthquake, occurring in some part of the world over the next 10, 50, 100 years, depending on the event. And the way this is typically done is by constructing large stochastic data sets, which are called stochastic catalogs, using statistical modeling and physical principles. Now, because we're talking about the probability of extremes, as you might imagine, the size of these data sets, the size of these catalogs, it has to be quite large for the probability estimates to be trustworthy, right? In addition, the requirements that we have from our clients, which are for the most part insurance and reinsurance companies, but also government institutions, these requirements are becoming more and more specific. For example, a decade ago, the type of question that a catastrophe model would be asked to answer would be something along the lines of, what is the probability of a Category 4 hurricane making landfall in Texas? Today, the requirements are more specific. And so we would be asked questions like, what is the probability of a Category 4 hurricane making landfall in Texas and spilling over Houston and dropping 50 inches of rain, right? It's way more precise. And I guess the current models that we have can get us closer to a good answer to those questions. The type of questions that we are not able to answer yet with confidence are questions along the lines of, what is the probability of such an event occurring in a different part of the country? For example, what is the probability of a Harvey type event occurring in Florida or North Carolina or Alabama? And the main difficulty in answering this question is that these extreme weather events are what we call in the industry jargon gray swans, which is kind of a cool hip term to describe an event which has very low probability of occurrence, but very high magnitude impact, which means, it's an extreme event, right? But the causes that trigger the event, the mechanisms that trigger the event are somewhat well understood. Like, we know the reasons why these things happen. And when we talk about extreme weather event, what that means is we understand the physics to some extent. For example, if you look at the Sandy event or the Harvey event, we know that these things were caused by what's called atmospheric blocking, which is a phenomenon where you have essentially two competing pressure systems. And so Sandy, and I think Harvey as well, got trapped between these two systems, and that's what made these two events very extreme. So we understand the physics of these things, but they occur with very low probability, right? They're very infrequent. More broadly speaking, extreme weather events are known to be caused by nonlinear interactions between scales, right? And this is a topic that has been discussed extensively over the past week, I guess, in a number of talks. And this is relevant to the catastrophe modeling industry from the perspective of generating large data sets, large stochastic catalogs, because you know, if you come to me and you ask me to generate a stochastic catalog, one thing that might answer to you is, I'm just going to pick up an off-the-shelf global circulation model, and I'm just going to run it for like 10,000 years or 50,000 years, numerical years, right, not physical years. And then if I run it for long enough, at one point, you'll see a Harvey-type event somewhere in Texas. You'll get what you want. You'll be able to compute your probabilities, right? Now, this is a fair answer, but the problem if you do this is you will at some point be confronted with the inherent limitations of GCMs, of global circulation models, which are precisely related to the issue of scale resolution and scale interaction, right? This is a figure that I think, Pedram, you used in your talk as well, that shows the type of physical phenomena that you might hope to resolve with a global circulation model, depending on the scales at which these phenomena occur. And I guess we all understand that scales that are below the resolution of the climate model will be unresolved. And this is problematic because it will lead to uncertainty in the output of the model, but also to potential biases. This is a figure taken from a review paper, I think, that shows the percentage of block days, so the number of days during which an atmospheric blocking event occurred versus longitude. And you have several lines on this plot. Each colored line refers to a particular GCM, a particular climate model. And those are compared to reanalysis data, which is the black dotted line. So reanalysis data, you know, it's widely used as a benchmark for reality. It's a combination of like a bunch of field measurements and I guess data simulation techniques and numerical models. So this is considered to be the ground truth, right? And what's clear from this plot is that the frequency of block days strongly depends on the type of climate model you use, and it also varies by longitude, which is, you know, when you're out to compute probabilities of occurrence is a problem, right? In particular, you can see that there is a severe low bias over Europe, which is problematic from the standpoint of quantifying European windstorms, I guess. The block events are also known to be severely overestimated at lower latitudes, I believe. And so your models are biased, right? So one thing that you can say when you see these things is, well, that's no problem. I'm just going to run the same climate model, but at higher resolution, right? And this is something that a large part of the climate modeling community has been working on for decades, I guess. If you go back to, you know, the 70s, initially the climate models were quite rudimentary, both in terms of the physical processes being modeled, but also in terms of the resolution. And then as time goes by, the sophistication of the models increased, the resolution as well. And this is a good thing, right? What is interesting is that it does not necessarily mean that you'll get closer to the truth by increasing the resolution. In fact, higher resolution climate models might improve some biases, but not others. So you'll still have some problems. It might also improve biases, but for the wrong reasons, or the wrong physical reasons, let's say. And all of this would occur at a higher computational cost, right? These things, you need like large machines to run these things if you're looking at very high spatial resolution. In addition, because we're talking about generating large stochastic catalogs, large data sets, you also have a storage problem, potentially, huge amount of data being produced. And so from the catastrophe modeler's perspective, running a GCM at high resolution is not a solution, right? It's just impractical. So there is a need, I guess, that we have identified for the design of a new framework, a new paradigm almost, right? For GCM simulation that is tailored to the purposes of the catastrophe modeling industry. And what that means is we'd like to have some tool that is computationally inexpensive to the extent that that's possible, and something that pays close attention to the extremes. This is really what we're after in the business. And so we think that this is kind of the idea of the project. A combination of statistics, physics, and machine learning can help us achieve just that. So I guess I'm not saying that GCMs are like low resolution or high resolution GCMs are completely should be dismissed entirely in this context. It's actually quite the opposite. In principle, you could still take your Coarse-Scale climate model and run it, produce a lot of data with it. And we know that these things that are based on physical principles, that are based on governing equations, there is some good physics in there, right? You're not starting from zero. And so from the perspective of generating catalogs, these things, if it's coarse enough, you can generate data quite quickly. So you're halfway there, right? The only problem is the bias problem. And so if you can fix that, you're in business. So we are actually going to use Coarse-Scale bias GCMs as a foundation for the framework that we're proposing, right? This will be kind of the basis for everything. So the idea that we're proposing, it's very simple, I guess. You start from a Coarse-Scale bias GCM, which runs fast, but is inaccurate. You feed that to a machine learning algorithm, and then you hope that out somehow the machine learning will debias it. So it will fix the statistical inaccuracies and the biased, the output, the debiased GCM will be also at a coarse scale, but it will have the right statistics of the extremes, right? It's very simple.
So not just ML though, you have to feed it observations.
Correct. So to determine whether or not the machine learning is doing a good job at debiasing, we need a target. We need the reference, right?
No, I'm saying it's not going to just debias it. The input to the ML also has to have observations because it has to learn the bias between the model and truth.
Yeah, so I guess that's what I mean by target. It's like, the machine learning algorithm will see, it'll have some knowledge of what an unbiased climate looks like. I think this is what you mean, right? Yeah, true. I guess, yeah, that's a good point. I guess this cartoon should be fixed, is your point, right?
Just to clarify, this is like a post-processing after running a GCM, or is this inside the GCM?
It's a post-processing. Yeah, I'll come back to that in a minute. Okay, good. So I guess, yeah, what I'm showing now should probably be shown on the input side of things. I'm showing it as a target, like something to compare to, right? And so the reference for the model to figure out whether or not, to figure out how to debias things will be reanalysis data, this, and the Coarse-Scale component of it. Again, because this is widely used as a benchmark. And this is the general idea, right? We just use ML to fix the biases of the output of the climate model. Now, I talked about nonlinear interactions between scales earlier, and we know that these things are also a driver for extremes. And in this picture so far, there is no notion of fine scales, right, which is an important component. So this is actually half of the picture of the framework we are proposing. We still need to deal with the fine scale somehow, not only on physical grounds, but also because there is really no such thing as a Coarse-Scale reanalysis product, right? I mean, these things are kind of fine in resolution. And so you have available as leftovers the fine scales from the reanalysis product somewhere that you can use, right? And this thing, the way we deal with the fine scales, you can think of it as a second step of the framework that will come downstream of the debiasing part. And the way we'll do it is in a very standard fashion. We will try to learn a parameterization between the fine scale reanalysis and the coarse scale reanalysis. I guess it's a very standard thing to do. We use our own kind of ad hoc algorithm to do this. And then once we have this parameterization between the fine scale and the coarse scale, we can feed that the output from the machine learning algorithm, the debiased business. And then that'll basically give you the corresponding fine scales associated with the output of step one.
So you mentioned that that's also learned. So the parameterization is instantiated by an ML model.
Correct.
Also, okay.
Mm-hmm. Is that clear so far?
So in this debiasing, are you fixing, like at what kind of time scale are you debiasing the GCM? Is it like a weather time scale or the statistics?
Statistics, and we're looking at physical concepts, I guess.
Okay.
So we're approaching the problem from a statistical angle, and I think this should become clear as I describe the type of loss functions we're using.
Sorry, I do just want to get this clear. You're not just coarse grading somehow or filtering.
No.
You're doing something else.
Correct.
From fine scale to coarse scale.
Yes.
You're doing that in part. Well, yeah. Why are you doing that?
You mean the splitting between fine and coarse?
No. Why aren't you simply coarse grading?
So how would coarse grading help the debiasing?
I'm asking only about the reanalysis piece.
Yes.
And the idea would just be, if you're asking what is the coarse scale reanalysis, why would you, I don't understand why that's not simply the coarse grained reanalysis.
Oh, you mean on the reanalysis side?
On the reanalysis.
Yeah, no. Oh, so then this is, yeah, you can think of it as coarse grading. For the reanalysis, for the processing of the reanalysis data, you can think of the splitting as coarse grading. That is, yeah, I thought that you were referring to the bottom part of the graph. Okay, yeah, that makes, yeah. We're not exactly doing coarse grading. We're using a wavelet decomposition, which I'll talk about in a minute, but same idea. Yeah, absolutely. Yeah.
Sorry, I just had a quick question. Even if your model was a perfect representation of the Earth, it wouldn't look like reanalysis because of just variability.
Correct. So I was exactly about to mention that point. So, you know, what you get out of the GCM is essentially a number of realizations, right? Stochastic realizations, they're ensembles, they're, you know, possible scenarios of what the climate might be, right? And so the target is reanalysis, but we're not trying to match reanalysis exactly. We're not doing forecasting, right? We're just trying to kind of nudge the output of the climate model so that statistically it'll look more like reanalysis in a statistical sense, right? So we won't be looking at pointwise agreement in space and time because that wouldn't make sense, right? You would just be reproducing the reanalysis data over and over again, which is not what we're after. Does that make sense? Yeah. Okay. All right, so in this talk, I won't be talking about the fine scale business. I'll just be focusing on the coarse scale path here, I guess. The fine scale, as I said, can be thought of as a downstream post-processing step. Okay, so we're talking about scale representation and scale separation, and I guess this is a good time for me to tell you a little bit about how we do this exactly, right? And the breaking down of scales is important from a physical perspective because we all know about, you know, the cascading of energy and turbulence, but it's also important because if you select the right representation of the spatial scales, you might be able to break down the problem into smaller pieces that are more manageable computationally, right? So there's kind of a nice side effect of that. In this work, we use a particular flavor of wavelet decomposition on a sphere, which provides essentially a discrete representation of the spatial scales. And this has multiple advantages. The first one is if you were to work on the native grid, or the native reanalysis grid, that's probably like, you know, hundreds of thousands of grid points. But if you do the wavelet decomposition, you reduce the dimensionality of the problem quite substantially. The wavelet decomposition, as with any decomposition, would provide you with I guess, an expansion of any field in terms of wavelet coefficients, right? And each wavelet coefficient would be associated with a particular center. You have this kind of hierarchy of scales, which are called levels. And for each wavelet center, denoted by the orange dots on the screen, you would have an associated wavelet coefficient, right? It's essentially, you can think of it as a basis expansion, right? And the third advantage is, in principle, it would allow us to solve the debiasing problem locally over a particular region of the globe. And the way you would do this is you would essentially zero out the wavelet coefficients outside of the region of interest, right? You can kind of surgically go in and decide exactly where you want to solve the debiasing problem.
So from level 1 to level 5, does the spread coefficient of the wavelet applied to the points decrease?
What do you mean by spread coefficient?
Well, it's, think of like a radial basis function or something.
No.
There's some kind of variance term. So are you covering the Earth with smaller wavelets?
Yeah, so
Okay.
it's on the next slide.
Then
actually.
on level 1.
Yep. Yeah, absolutely. Yeah. So, yeah, I'm glad you're bringing that up because there are a number of properties, let's say, of the type of wavelets we're using that I think are worth mentioning. This is what the wavelets look like, right? From level 1 through 5, I guess. One nice thing about this particular spherical wavelet framework is that the wavelets are well localized in space and frequency. They're essentially, their spatial distribution is essentially as isotropic as it gets, right? And what's nice about this is that you get very good coverage of the poles, which, as I understand, is an area which is kind of notoriously difficult to capture with wavelets. But we're able to do it, I guess. The other thing is that the wavelet decomposition provides you with a discrete Parseval type frame for functions that are square integrable over the sphere, functions that have finite energy. And what that means mathematically is that you have well-defined, well-behaved formulas for projection and transformation, projection and reconstruction between wavelet space and physical space. This is very reminiscent of what you would get with an orthonormal basis in linear algebra, except it's not exactly a basis, similar in spirit. An indirect consequence of the Parseval property is that the wavelet decomposition comes equipped with a simple quadrature rule, which, if you're a numerical methods person, is always nice to have, I guess. I mean, I like it. I think it's cool. And the last thing is these wavelets have been found to have good conservation properties of energy and entropy in the shallow water equation. So I'm not making the claim that this is true for every single PDE that you might want to project on the wavelet frame. But for the shallow water equations, we found this good conservation properties. And it just gives us confidence that this is a good decomposition for us to use because the shallow water equations are essentially a simplified version of, the climate, I guess, roughly speaking. Okay, so now we got that covered. Let me get a little bit more specific about the climate data sets that we're using. For the bias this is what we're using in the numerical experiments so far, right? For the bias GCM, we use the SPEEDY model, which is an 8-layer spectral model. It's fairly standard. You have all your primitive variables, UV, vorticity, etc. And we have available 25 SPEEDY runs, 25 realizations, 25 simulations, each of them being 40 years long, right? On the reanalysis side, we're using the RF5 product, which is a 3-hourly historical record that goes from 1979 to 2018, right? And at the bottom, I'm showing, these are snapshots for now. This is vorticity close to the ocean surface. And the reason I'm showing these is that you can almost see, the biases in SPEEDY, right? So the purpose of the machine learning algorithm will be to take all of these 25 SPEEDY realizations and then deform them or do something with them so that they will look more like the reanalysis data. Again, not pointwise in space and time. We don't want to reproduce what's on the right. We just want to correct the statistics and maybe the spatial patterns, wave propagation, things like this. You can clearly see how these two are qualitatively different, right? They shouldn't be compared, one-to-one again, but you can clearly see that in SPEEDY you have maybe longer blobs, right? I mean, the propagation of stuff is not really realistic compared to the ground truth, right? Good.
What is the horizontal resolution of SPEEDY?
I think native, it's about 10 times as coarse as the native grid of Verify. And then, but we make sure that this is on the same grid, right? Good. Okay, so I think we're now in a position to formulate the problem in a way which is a little bit more rigorous. This is the cartoon from earlier, right? We're asking the machine learning algorithm to fix the biases. So with the wavelet decomposition and, that I described earlier, what you're really working with is on the input side, a set of wavelet coefficients, right? A bunch of time series from this PD model. And on the output side, you have essentially the same thing for the R5 data. Both data sets have been wavelet decomposed. One thing that I should make very clear, I should have made very clear earlier, is that when I'm saying debiasing the climate model, we're not, the climate model is a set of PDEs, right? It's governing equations. We're not going to alter the model itself. We're not adding closure terms or anything like that. We are debiasing the output of the climate model. So just the time, working with time series only. And then the ML algorithm is just a map, right? So we formulate the debiasing problem as an unsupervised learning problem. And because we're working with time series, it makes sense for the machine learning algorithm to be the machine learning architecture to be suitable for time series manipulation. So we've experimented with LSTM, long short-term memory neural nets, and temporal convolutional networks. And mathematically, this takes the form that's shown on the left. What arises kind of naturally out of these two architectures is the presence of this time delay parameter, which is kind of up to the user's discretion, right? The choice should be made based on, I guess, physical considerations, right? And I guess if you're coming from a dynamical systems perspective, one way to think about this formulation here is, what the time delay does is essentially embedding the time series into a different space, right? It's an embedding process. And so what we're essentially doing is, you can think of it as the speedy data is evolving on an attractor of its own, right? It has its own phase space. It's chaotic. And what the machine learning will do is excise from that chaotic attractor small chunks of trajectories, small filaments of trajectories. That's what the delay is about. And it'll transport that onto a different phase space of its own, which is where the R5 attractor lives, right? Conceptually, it's kind of like that. And what we'll do is that we'll require the shape and the statistics of that deformed attractor to be the same as the R5 attractor. Does that make sense? Oops.
You're setting up, are you setting up an auto regression task and hoping that you'll just get debiasing out of that without any link to unbiased data? Or
I think, okay, that should become clear on the next slide. So during training, we are comparing to reanalysis to figure out whether or not the output of, whether or not Y has been debiased, right? I think, yeah, I guess your question is like, it's about understanding how this can be formulated as a supervised learning problem. I think it's going to be the key point. Okay, hopefully this will clarify things a little bit. Let me go back here real quick. Okay, so, we're working with time series here, and these are wavelet coefficients, right? So if you remember the globes with the orange dots, on each side of this map, you have about maybe, 2,500 time series to work with. So ideally, in principle, what you'd like to do, you'd like to feed this 2,500 dimensional vector to the machine learning and ask it to figure out how to debias the whole thing, right? So it's like having a gigantic model. We've tried it, and what we found is that it's quite difficult to train just because of the sheer number of variables that you're presenting the network with. And it's computationally expensive to train, but it's also difficult for the network, for the model to figure out what it should do. And on physical grounds, I guess it makes sense because if you're presenting it with all the wavelet coefficients from all the scales from all across the globe, it has to figure out that there are probably, connections between certain coefficients that don't matter, right? Teleconnections, I guess. It has to figure out that on its own, which is somewhat difficult. So what we did instead was we went for I guess a divide and conquer approach, as you might call it. So here's how it works. On the input side, we consider a particular wavelet center, which is the central blue dot, and the neighboring points, right? We feed that to a small network. This is a smaller model. And we ask the network to produce an output for the central point. So this is for a point over Germany. And you can do the same thing for a point over Iceland. And the same thing for a point over Spain. And you can essentially do the same thing for every single wavelet coefficient that you have. You can cover the entire globe with models. And each model will be in charge of its own little sector, right? And then you would combine the outputs of all of these models and compare them to something that doesn't have any biases, right? I think that's clear where your question was. You need somehow to show the network what an unbiased climate looks like. And this is done through the loss function. This comparison between the output and the reanalysis is done through the loss function. Now, in principle, I guess with the loss function, this will have to have two components. One which is statistically oriented, because this is what biases are about, and another component which contains some physics. We want to make sure that the output of this army of models is consistent or produces is realistic enough, right?
So you have an ensemble of GCM hindcasts, and then you have the corresponding reanalysis data for each training image?
Yes.
Okay.
Other questions? All right, so when you put all these models together, when you put all the red dots together to produce a field, I guess, one thing that you need to pay close attention to is whether or not these models are communicating during training. In principle, if you don't have them communicate, chances are you'll get garbage out when you go back to physical space. So these models are trained concurrently, and this is done essentially through the loss function. So as I said before, we use two types of loss functions because we are after statistics and physics. So on the statistical side, we'll be looking at something that we call the PDF loss because it targets heavy tails and extremes. The formula on the far right doesn't show the loss function itself. It's about the quantity that we put inside the loss function. So any loss function that we use will be essentially that quantity computed for the output of the network and the same quantity computed from the reanalysis data. So the PDF loss will take care of the extremes. We'll also look at the cross-spectrum loss, which is essentially a product of Fourier transforms. And this takes care of the cross correlations between the models outputs. This is one of the two loss functions we use that require cross communication between models during training. A third kind of more surgical version of the cross spectrum is the bispectrum loss, which is, you can think of it as essentially the same thing, except it's higher order, right? It's like more nonlinear. This one doesn't require cross communication. And then the fourth loss function is what we call the energy loss, which serves as a physical regularizer. So right now we're just looking at a simple norm, L2 norm for the fields. This is a global quantity defined over the entire globe. And so this also enforces some sort of communication between models. I'll skip this slide real quick. This is more for those of you who are computationally oriented, I guess. This is how we dealt with out of memory issues, but I'm out of time almost. So, all right. So now let's take a step back, and then I'll move on to the results and ask ourselves, why are we doing things this way? What's the purpose of this architecture? And as you might have noticed so far, as I'm describing this training procedure, I haven't referred to any sort of physical variables yet. I haven't talked about, atmospheric levels or anything like that. And this was on purpose. I mean, the real value of this framework is that you can use the architecture I described as a building block. And so you can start with, let's say, a single variable at a single atmospheric level and train a series of models on that, and then add more to it, right? So the architecture in principle can carry over across scales, across physical variables, and across atmospheric levels. And what you get out is essentially that's the kind of the end goal, is to get a multi-hazard view of risk in any arbitrary region of the globe. Good, so where are we right now? As I said, it's ongoing work. Currently, we're looking at vorticity close to the ocean surface. This is sigma level 0.95, I believe. So one variable, one level, pretty simple. So this is what it looks like. Let me pause it real quick. Here, the models, this series of models, has been presented with 5 speedy runs, 5 speedy realizations. So it's been trained on that. And now we test it on unseen data, right? Like on the 6th run, and we see how good it's doing at debiasing it. So you have, again, it's vorticity. You have the speedy output here. This is, let's say a representation of the network. The debias is here, and the target is at the top. Again, we're not looking for point-wise agreement in time between debias and reanalysis. We're just looking to improve the spatial patterns, I guess. And, I think we're not doing a terrible job. I mean, we're not quite there yet, but we're probably 80% of the way. And, you have some advection that's going on. You have some of the blob structure is also fixed to some extent. The real test, though, is if you look at time series for certain cities, let's say. These are in physical space for Munich on the left and Istanbul on the right. Speed is at the top. The debiased one is in the middle. Arrow 5 down there. The job of the network is to essentially take the blue line, make it look like more the green line, right? It's not too bad. We get the extremes quite well. This is something you can see a little better on the following slide. These are marginal densities and spectra for the 2 cities, the set of time series I just showed. And again, you want the orange line and the green line to get closer to each other. This is the job of the network. And it's not, if you look at the tails of the PDFs especially, we're not doing too bad of a job. These are mean vorticity fields. This one is kind of easy to get. So you get very good agreement between the debias and the reanalysis, although this is not really the target, I guess. But because we're getting the spectra so well, the 0 component of the frequency spectrum, we get good agreement there. I'll leave the conclusions up there. I'd be happy to take any questions. I just want to mention before I close out that we think that the 10-20% remaining they probably have something to do with the physics. Right now we are penalizing the physics in a weak way, I guess. We could be a little more aggressive there. And so this is what we're working on right now. Thank you.
We have time for some questions. Moment, go ahead.
Sure. I have 2, basically. One is, okay, I have 2 questions. One is, so if your GCM is biased, okay, but what is if Its Lorentz attractor never gets the variability you need. So especially for the problems you're looking at, like blocking, essentially problem of redistributed momentum, right, in zonal. And so gravity wave tracking, these things are important. And if you have a biased model that never gets the attractor there, you don't have the signal. You cannot translate between the attractors. And I wonder how you want to overcome that.
Yeah, so I mean, one thing that you could do, it's essentially, I guess the broader question is, if there is a physical something that is not present in the model, what hope is there that the neural net will be able to create that out of the blue, right?
Yeah.
And I mean, that's a good question. So far we think that, the models have, enough information that if we fix the statistics, we'll get something that looks good out. If that's not the case, if there is some fundamental flaw in the model, for example, as you're describing it, one thing that we could do is add a little bit of, stochastic perturbation to what we have now. We need to think about the technicalities of that, but the idea would have to have like an additional model that would essentially pump in energy or something along those lines that would take care of the phenomena that you're describing. So this, if I guess, put it another way, if what you're describing arises, this framework will have to be adjusted a tiny bit. It won't be able to take care of it on its own.
Yes, but okay. Second problem, which is kind of a similar point. So you want a probabilistic idea, right? You don't not necessarily interested in the phase at the end, but you don't want to get the phase right of your stuff in error 5, but you want more like a probabilistic representation of the extremes, right? A likelihood or whatever. But your performance metrics, you showed like a power spectra, but at the end, what makes the extreme of the surface is the coherency, right? The phase information, the stuff that sits like at the same position. And you lose this phase information if you look at power spectra, right? So you
correct. That's a very, yeah. So okay, let me go back to the loss function thing. So that's one thing that we observed, I guess, fairly early on, is that, if you're looking only at spectrum amplitude, like how the energy distributed, you lose the phase information and you end up essentially with standing waves in the output. Like there is, there might be no wave propagation at all. The way we address that right now, and it's not perfect, but it's one way to get there, is through the cross spectrum. So what the cross spectrum loss does is you're looking at a particular wavelet center and you're computing the cross spectrum of that center with its neighbors. And there is like, you can choose however many neighbors you want to look at. And the cross spectrum loss, it's a complex quantity. It's not the cross spectrum amplitude loss. So, it's the product of two Fourier transforms. The phase information is in there. The amplitude information is in there. If you just retain the amplitude information and do away with the phase, standing waves all over, and we don't want that. So we're computing the full complex quantity here.
we compute the loss in the complex phase space.
So again?
Compute the loss in the complex plane, basically.
That's right. Yeah. So real and imaginary parts, try to match the two. You can also take the arctant or whatever. No.
Okay.
Okay, Duncan.
Yeah, thank you very much. Given obviously, you intend to use this for climate change risk analysis and presumably, quantifying how those risks will change into the future, how robust do you feel this approach is, or how do you intend to handle potential changes in the dynamics under a changing climate?
Okay, so this framework is not exactly intended to address the question of climate change, but it can to some extent. And the easy way to do this is to essentially do subsampling of the output of this thing. So, if you have a long biased GCM catalog, you run it through the framework that I described, and you get a long unbiased catalog out. And then you would essentially subsample that catalog based on you know, what you observe of the climate currently or the trends that you're expecting. So the keyword here would be subsampling the output of this thing.
But it would still have to be a state that you've observed in a reanalysis, right? You wouldn't be able to go very far outside the observed.
That's right. So in principle, you would be, that's absolutely true. You would be able to get, I guess, reasonable predictions not too far out in the future. Yeah. Cool. Again, not exactly the purpose of the framework. So there's probably some work that needs to be done on that front as well.
Thanks.
Thank you.
Hey, great. Let's thank Antoine again.
Thank you.